as we've done in many cases, before we talk about what we'll do today, maybe it's good to recap on what we have dealt with in the past, because we kind of closed out a topic. And so I'm going to try again just using this 10-speed run-through for the previous 2017 lecture, so 2 years ago, not 1 year ago. And I will personally narrate it as it goes through. And so the focus of what we're trying to do is trying to understand the rates at which fluids will move as two separate fluids. And to do that, we needed to accommodate some basic characteristics. And the basic characteristics were related to capillary pressure saturation curves and relative perm curves. Those are the two sets of data that we used. And those place into context if we look at the subsurface, going from the surface, water table, and below. Look at the pressures that would be there in a static column of DNAPL red, water blue, and air green. The air above the water table, and the water below the water table. And according to those pressures, the differences between water pressure and air pressure above the water table and water pressure and DNAPL pressure below the water table, we can define those capillary pressures changing with depth, and you've done an assignment to deal with that, and draw the capillary pressure versus saturation curves, which are shown on the right-hand side. And they're characteristic, but they're flipped. One's the mirror image of the other one. And they really define how the saturation changes from at the water table to be quite high saturation of water and a reduced saturation of water as you go up to the ground surface. And below that, below the water table, a high saturation of water close to the water table and a reduced saturation as you get deeper because the DNAPL can penetrate. And so we rationalized everything that we can do based on those capillary pressure versus saturation curves. So those are key understandings for us. Also related to those, and on the same axes, if you like, are how the permeability changes. So the capillary pressure curves say something about the static behavior of fluid when it's held in equilibrium by meniscus forces. And the relative permeability curves say something about the rate at which it can move in the subsurface. And the two are related because you can draw one on top of the other. And they're related through the residual saturations of water and the non-wetting fluid. Non-wetting fluid can be air or it can be water. Can be NAPL rather. And based on those limits, those two saturation limits, then that defines the relative permeability curves, which kind of looks like an X, if you look at it, in terms of the water relative permeability shown in blue and the NAPL permeability with a bit of hesitation shown in red, I think. That's why it was going fast. And based on those, we can define Darcy's law. And Darcy's law allows us to use these relative permeabilities to calculate fluid flow-through rates within these systems. So that's basically what we've attempted to do. If you haven't looked at it already, last Thursday's presentation was about some different ways of being able to characterize this term, relative permeability, as a function of saturation in a very practical sense related to the gradation of soils. So finer gradation soils and coarser gradation soils will have characteristically different relative permeability and capillary pressure curves, and we can define those. So that's basically what last session's discussion was, to top off this idea of the fact that we can look at these two fundamental characteristics. So we're going to leave that behind now, and our interest now is in being able to now look at transport once it's in place. So this idea that we had before, it's covered quite nice diagrams, is that once we get this non-aqueous phase liquid in place, it stays there because it's held by capillary pressures and meniscus forces. Its location may be as pools and also as these smeared chimneys, if you like. And certainly water can flow through this in the saturated zone and will dissolve components of it. And the rate at which it can remove this is controlled in some respects by its solubility, but also by the rate at which fluid can go through it. And so what we'll look at now are the mechanisms by which this stuff, which is ostensibly anchored in place, not going anywhere as a free phase, is very difficult to move as a free phase because you can't suck it out because it's held in so strongly by surface tension forces. What are the consequences of that? If it doesn't dissolve at all, then there aren't really very many consequences because it would stay in place. Nothing would dissolve in water. The water that goes through it would be pristine when it comes out the other side, and we wouldn't have to worry about it. But that's not the case. It does dissolve, and therefore we do have to worry about the amounts that get carried downstream. So basically we're interested in being able to understand what are the magnitudes of the components that come out of this. And I suppose in particular two themes. Rates of transport and residence time distributions. Times or distributions. And those are relatively straightforward ideas. We know that rates of transport, we can calculate the Darcy velocity. So if we want to get the mass rate of transport, I'll just write it out, is going to be equal to the Darcy velocity multiplied by some cross-sectional area multiplied by concentration. And if we look at the units of that, Darcy's velocity, which comes from Darcy's law, so V sub D is equal to K over mu relative permeability and the pressure gradient, kind of, right? If you can see that. And if you look at the units of this, Darcy's velocity is in meters a second, area, cross-sectional area is in meters squared, and concentration is in some mass per unit volume. And so out of these disappear, and we have a loading in terms of mass per unit time. So simply we'd like to be able to figure that one out. And so we can probably do that so long as we can calculate what Darcy's velocity is. And residence time distribution we can write as time of arrival, and that is advective flow velocity is equal to, I'll write it just over a bit, is equal to the Darcy velocity divided through by porosity, which is equal to the advective velocity, which is equal to the length traveled in a given time. And so if you look at flow along a core, which is kind of the geometry that we'll probably look at here, this is the length traveled. This is the Darcy velocity, which is the one that's over this area. This is the cross-sectional area flow, which I guess we talked about here. So we talked about that. Concentration is whatever the fluid is. And this is length. And so in other words, the arrival time is going to be equal to length multiplied by advective velocity and time, quite simply, just by rearranging this. Or the time taken to arrive somewhere is going to be equal to the length divided by the advective velocity. So you've used these already in your first assignment, basically, right? And so this basically says how long it takes for a front that's moving down along this system in terms of some relative concentration. How long it takes for this front to physically move. And so this would be the length traveled at any given time. So this would be, I guess, length traveled. Maybe you should do this. And this would be the concentration of the stuff as it goes downstream. So unit concentration, if this is relative concentration upstream, then this is between 0 and 1, just conveniently. This is the location of the front. It could be a plug flow front or not. We can talk about that a bit now. But basically the two things that we'd like to figure out are these two items here. How quickly what mass rate gets carried downstream for two reasons. One, because that's the rate at which this is depleted, and also it's the rate at which it arrives at some compliance location. So that's of interest for that. And this says something about when it arrives. Does it arrive tomorrow? Does it arrive 10 years from now? 1,000 years from now? Is it already there? Depending on the system. So that's kind of our interests in this, to put it in context. Okay. So to do that, these are the things that we'll talk about. We put it in context for last time, talking about the Van Genuchten relations, etc. We'd like to talk about the different mechanisms by which transport occurs, and the principal ones are by diffusion and by advection. We've only just talked about advection. We haven't really talked about diffusion, but diffusion is an important mechanism as well. And it turns out that diffusion is only part of the picture, because most of diffusion is really driven by these concepts of mechanical or hydrodynamic dispersion. And so we'll discuss that in due course. So what we'll do is we'll talk about transport, and it's important to realize that the transport we're talking about now no longer deals with the movement of the napple in the subsurface, but it is the rate at which this red stuff is getting dissolved out of here and carried, dissolved in water as an aqueous component, and is carried downstream to some compliant point. So the red stuff isn't moving as free phase, it's being dissolved and it's being carried downstream. And so that's our goal in this. So, what do we need to deal with? There are two mechanisms that we've just alluded to, and they're kind of shown here. The first one we've kind of described, that's advection. And so the description I always apply to this is that if I take a beaker that's filled with water, and if I put a drop of ink in there as some contaminant, and then I walk this beaker across the room in front of you, then that's physically moving with me at the velocity that I travel at, which is v sub a, the advective velocity. And that's physically what advection is. As that happens, also in that beaker, that blob of water is moving inside the beaker by diffusion. And so if you think about drawing a cross-section across the drop of ink in milk, then it would look like a skyscraper. This would be the direction radially across it. This would be the height of the blob as it sits there. And if diffusion didn't operate, then nothing would happen. But if diffusion does operate, then you'd expect after some time the distribution of this to look slightly different. And after even further time has elapsed, it looks even flatter. It goes across here. And that's the process of diffusion. And physically, really what it's doing is it's taking this gradient of concentration, which you see here, which if I draw this, which would be dc in this direction and dx in this direction. And it's that gradient that is driving the diffusion through Fick's law, which we'll talk about. And so that's a mechanism that occurs just due to molecular diffusion. But if you look within an aquifer, where we're not talking about just a beaker, the other thing that goes on is dispersion, which is diffusion-like. And so if you didn't know what was going on and you looked at the snapshots of the distribution of concentration at time 0, which is the blue here, and time 1, which was the red here, and you just saw those two snapshots, you wouldn't be able to tell whether it was occurring due to diffusion or dispersion because they look identical to each other. But dispersion is physically a different process. And the idea is this. You start off upstream with this Manhattan skyline distribution, a single blob of the fluid. And as it goes downstream, it mixes, it goes down different tortuous paths. And if you look at it as it's downstream, then all of a sudden it's spread out. And so if you didn't know that you've moved from upstream to downstream, you wouldn't know that it's mechanical mixing. It just looks like the same process, which is diffusion. And so when you look at transport in the subsurface, we are interested, I guess, in both of these processes. And they operate in different circumstances. Diffusion acts when the physical motion of the flow is so slow that the only spreading mechanism is by molecular diffusion, Brownian motion. And dispersion, conversely, operates when the flow velocities are large, the mixing in terms of going up and down different pore routes is varied, and therefore the mechanical mixing completely dominates over diffusion. Diffusion would still act in this place, in this circumstance, but it would be completely dominated by the mechanical mixing effect, which would not allow it to show up. Because these effects typically act very slowly. And so what we'd like to do is be able to address both of these processes. So I'm sure you've seen it in your background, that diffusion responds to, or Fick's law Fick's first law is a representation of diffusion. And it really follows what we've just said about this concentration due to an ink drop, which has infinite concentration at the boundaries of the blob, and zero concentrations outside it, and zero concentrations in the middle of it. And this infinite concentration gradient is something that nature hates, tries to get rid of, and it gets rid of by causing diffusion to occur. And the statement of that is Fick's law, which says that the mass flux, the amount of dissolved mass that is moved in the system, is proportional to the gradient of the concentration, dc dx. Concentration has units of, as we said, mass per unit volume typically. And length is units of length. And the diffusion coefficient, typically in units of length squared over time, meters squared per second, is the coefficient that describes that behavior. It describes it in a beaker, where this would be the diffusion coefficient of salt in water, for instance, or a salt solution in water. And the negative sign just means the fact that the direction of the mass flux is in the opposite direction of the gradient. And so if this is a positive concentration here, this is a positive distance here, then this is a negative gradient, right, by definition. A gradient dc dx in this direction is negative, but the mass flow is in this direction. And so this negative sign represents that. And so what we typically do is we want to be able to look at diffusion. It's not very interesting if you look at it just at a point, but we want to be able to say how it contributes to this behavior in a flow field. And so what we do is we use a conservation equation. And the conservation equation says mass rate of flow is equal to mass accumulation. And so that's also simply stated, the mass of accumulation is equal to mass in minus mass out. Nothing more than that. We don't really need to worry about these equations too much, I don't think, in this class. We'll note that they exist because they're used to determine how behavior occurs at field scale. But what we can do is into this conservation equation, we can put these fluxes, which we can define in each of the x direction, the y direction, and the z direction, driven by the gradients in each of those directions. And we end up with this expression from that. And if we simplify it, we end up with fixed second law, which is just this conservation equation. So this again is mass accumulation equal to mass in minus mass out. And it's controlled by this term. So everything that we've done so far, including getting rid of this term, which represents porosity, has assumed we're sitting in a beaker. No porous medium at all. And so this would be the coefficient that represents perfume spreading in air, for instance. In other words, where there's nothing that's blocking its flow, it's just in an open chamber or in a swimming pool or in a beaker. If you look at the behavior in the subsurface, then no longer can this diffusion, this Gaussian distribution curve, develop, allowing it to spread out without impedance from the grains, which describe the pore throats. And so schematically, if you think about it spreading within a porous medium, then the flow has to occur, and it has to occur in the spaces only between the grains as it travels downstream. And so this curve, this Gaussian distribution, would occur as it goes, I guess in this case, in both directions, right? You put it here and it spreads in each of these directions, but it can only go in the place where the water exists. So this tortuosity means that some of the cross-sectional area that it would like to flow in is restricted. The diffusion lengths become longer because they have to go in this circuitous flow path. And so you might expect that the effective diffusion coefficient in a porous medium is equal to the free diffusion coefficient of perfume in air or salt in water multiplied through by some coefficient which reduces it, that accounts for the fact that it has to go longer between upstream and downstream, that accounts for this diffusion length. And we can do that. And so we'd expect that this number is less than 1, and it turns out to be considerably less than 1, could be 1/100 of 1, and represents the fact that these flow paths are quite tortuous. And of course, we could measure that by making these diffusion measurements directly in the porous medium rather than doing it in a room, like here, like you can do here. So the utility of being able to define this diffusion equation, which is what we wrote 1 page ago, is that this allows us to be able to say how concentration would change at time at a particular location. And so if we do, for instance, have this system that we're talking about, which is upstream to downstream flow driven by Darcy flow and the advective flow, then what we'd like to be able to say is what is the concentration as a function of time, maybe at this location, some compliance location where we're standing. And the means to do that is to take this expression here and apply boundary conditions to it and a geometry. And typically the geometry that we would supply would be one that would look like this, that would say something about the distance downstream from some location where we have a concentration, and that upstream we apply some kind of boundary condition that defines as a function of time the concentration that we apply, which might look like this, right? In other words, you just turn it on at some time t0. Actually, that's what this figure here is exactly saying. and we'd like to know exactly what the pathway, which we did in green before, along this length, what the concentration would look like along this length. We've always used this Stark plug flow behavior to describe behavior, but of course that has nothing to do with diffusion whatsoever, right? That's advection. And so we'd like to know exactly what this front would look like. It's not going to look vertical. And we'd also like to know how quickly that would be traveling downstream, because that would say something about when it would arrive here. And so without getting into it, we describe a geometry, we describe some boundary conditions, and that are that the concentration of this system is 0 initially, and at some stage, time 0, all of a sudden we make it equal to C0, and we hold it at that magnitude for times greater than that. And if we solve it for those boundary conditions, which are really just the boundary conditions of putting the concentration equal to 1 at the upstream location and holding it there forever, and of course it looks like it's representing this case here, right? I suppose if we would represent that here, physically what we would be describing would be something that would look like this, right? That this is the upstream concentration, which is the red stuff, which is turned on at unit time, and would allow this pulse to look like something as it goes downstream, going from 1 to 0. Probably a bit small, but you can see that. Actually not small at all. And so that's what we're trying to represent. And it turns out that if you solve the differential equation for those boundary conditions, you get something that looks like a cumulative probability distribution. Not quite the bell curve in this geometry, but the cumulative portion of the bell curve. And so you know that a standard distribution function looks like this. Not very well drawn, right? And so if you started summing up the areas under this curve from this point to the right, then this area here would give you, and subtracting it, actually let me do it from the other side, just because it's congruent with this. So you start summing it in this direction going to the left, then this total area would represent a number here relative to its location, x. And then if you go a bit further, say to the middle point, then it would represent this area A2, which would be equal to this point here. And if you do the rest of it, up to this point here, then you'd end up at this point here. So this would be A3, A2, A1, etc. And so this represents the rate at which spreading occurs out from here. And this represents the cumulative distribution curve. And this actually is the profile that you'd expect to see as you go away from the location where you provide the upstream concentration on this boundary. And as you go some distance away, it wouldn't even have arrived. Actually, it would be present there at an infinitesimally small magnitude. If you go closer in, it would have got a higher concentration. And if you go right next door to the source, then it's almost at the concentration of the source. So this represents the distribution of concentration as you go physically away from it. And so what it allows us to do is be able to say when it would arrive. So you could define how the concentration at this point would change as a function of time and location. That's really so. And it conforms to this expression here. Complementary error function, just a mathematical function. It's a function of location downstream, the time when you want to calculate the concentration, and the magnitude of this effective diffusion coefficient. Those are the only things that control it. And so this expression here is what is physically drawn out in the figure at the bottom of the page this year. So concentration as a function of location and time, given the diffusion coefficient in the aquifer, what the time is when you're, this is a snapshot for one time. So this curve is for time equal, I don't know, 10 days. It's not, but it could be, for one particular time. And if you looked at what that curve would look like in 20 days, then I suppose it would look something like this. And you can calculate it from here. All that would change would be the magnitude of this, and you just put a whole bunch of x's in there to do it. So, pretty straightforward. So that describes one of our behaviors. So we said that we were interested in understanding the behavior in two modes. Those two modes are diffusion and dispersion. Diffusion is Brownian motion. Dispersion we gave an explanation for based on this spreading, but so far in our characterization when we talked about D star, we've really only talked about Fick's law and using diffusion to be able to do that. And so we haven't necessarily talked in much detail about this. The other mechanism that we can accommodate in a more sophisticated way than looking just at this behavior that we alluded to here. So this behavior that we alluded to here is that if we go downstream, everything that you said so far would say that we'd expect the plume to look like this, a step front for plug flow. We drew it in this as this green part where we have diffusion acting. So how do we now reconcile this behavior that includes diffusion with the behavior that we have where we have plug flow of the front moving as well? And so what we'd like to do is be able to combine both diffusion and advection together by looking separately at advection, and then be able to combine them in a single form. So, advection. We know something about it. We've talked already this afternoon about it. And that is that it's controlled by advective velocity, which is Darcy's law divided through by porosity. So this red part here is the Darcy velocity as we define it. And the advective velocity is just that divided by the porosity. In other words, if you have a pipe with a certain volume of fluid flowing through it, it goes at some velocity. If you stub off the cross section, so 95% of that, so if 99% of that pipe is closed off and it now flows at the same volume rate through now 1% of it, it travels 100 times faster. So that's just really what the difference between Darcy velocity is, full pipe, 1% left after it's closed off because of the cross-section area of the grains, is the advective flow. In the same way that we define the mass flux that's moving by diffusion in Fick's law, we can also define it in terms of advection. This is the product of advective velocity and porosity. So this actually is the Darcy flow rate, as it turns out. And if we multiply that Darcy flow rate by the concentration, just as we said before, this is equal to length over time and mass over length cubed. And so this gives us, if we want to know the mass per unit area, we then pre-multiply it by an area. This is a length squared, and this comes out to be just mass over time. Because the mass per unit volume cancels out with the terms on the top. Right? And this is the same as we defined as mass flow rate from before, nothing more. And so what we could do is we can take the same conservation equation, accumulation is equal to mass in minus mass out. They're actually mass rates, I think, rather than masses. They're mass rates. They have to be mass rates because this is in mass per unit volume per unit time, just from the units. And if we substitute this in here, by the way, I'll never ask you to reproduce these equations, but you'll see them everywhere in the groundwater literature, so it's probably useful that you know they exist. If we substitute this in here, we end up with an expression which is this, and if we simplify it, we end up with what is referred to as an advection equation. And so this advection equation, not surprisingly, says something about the rates at which masses are advected downstream. It's a little bit complementary to our diffusion equation. So this, where did we do it? There was one before this, right? This is our diffusion equation. And so if we take the terms that represent diffusion, and if we take the terms that represent advection, then we end up with a combined equation. And actually I will write it out just because it's important. And just in 1D, it looks something like this. Rates of change of concentration with time are equal to the effective diffusion, a second order partial with respect to x squared, minus advective velocity multiplied by a rate of change of concentration with location, first order. And just to make the case, this is accumulation, so this is mass accumulation. And it's a rate is equal to the diffusion rate, the rate at which mass is diffused into or out of the system, plus the advection rate. Seems strange that we add the terms together, but, because this is a positive sign here and this is a negative sign here. But in terms of what it physically means, is it's the mass that accumulates due to being diffused in the system and being advected in the system. And so that's not particularly important, but to understand physically what these expressions represent. And that is that it turns out that this equation, if, for instance, diffusion is 0, this expression only is a first order in space and a first order in time. It turns out to be a difficult problem to solve mathematically using numerical models, except for the conceptual idea that physically what this means is exactly what you've dealt with before. And that is, if you look at flow along a pipe, so this is kind of the geometry that we've looked at before. What you've looked at is, I'm going to draw these two little graphs, upstream and downstream. It's important you understand the concepts, not the equations. These are with time and concentration. Everything is with concentration. And along the length of this, this is with location. And so you know from what we've talked about in the past that if you all of a sudden turn on the upstream concentration with time, so in other words, you put the boundary condition on the end of this core from 0 concentration to, from water to ink-filled water at time t0. then if you look at the concentration as it goes downstream and it's advecting, then you'd expect it to look like this, where this is the length that it travels. And what is it? Velocity equals length over time. So length will equal the advective velocity times time. So that's this, right? This is how far it goes down. And if you look at the downstream part, then the arrival of this downstream is going to be some time here, which I suppose in rearranging this would be equal to length over velocity, right? And this is t traveled, I suppose, tt. So it's in its most rudimentary form, that's what we're attempting to understand. So you make the boundary condition here, turn it on at time 0, t0. Stuff travels downstream. If it travels as plug flow, you can calculate how far it goes in a given time. And you can also find out at a given time what the concentration is, either whether it's arrived, which would be after this point here, or whether it hasn't arrived yet. And so this expression that we've suggested down at the bottom, this advection dispersion equation, is exactly what describes that process. And the process that we've just explored is one where we turn off the diffusive term. And so by definition, it's a plug flow, and we can calculate exactly where along the length of that core that front would be. If, though, we now go back and remove this, and now we include this value of d star, all of a sudden there's a new term in that. Physically, what does that mean? Well, we saw that before, the physical manifestation of diffusion was that it doesn't have a sharp front, but it has this flat, canted over profile due to molecular diffusion. And so I suppose if you think in the opposite, if advection is 0, then diffusion will look like this. So what happens if you had advection, which carries the front to some location downstream, but also operating on top of that, you have diffusion acting as well. You'd expect to have this family of curves. So this would be where d star, in this equation at the bottom, is greater than 0. The red curve is where d star is equal 0. And this curve here would be where d star, the dispersion coefficient, is much greater than 0. In other words, you can think of this as a increasing magnitude of diffusion, as it says here, increasing diffusion. So I won't do that. I guess I don't even need to put that in, do I? So if you increase the amount of diffusion, you'll get progressively, you'll go from plug flow to, plug flow to this way, right? I guess if you're looking at it on the board. And that's all it is. So the equation allows us to be able to represent those behaviors. That pretty well represents the behavior we'd expect to see if we have this geometry here. And this geometry here is that upstream, the stuff is present as free phase in the pore space. It's dissolving out into the water. As it dissolves in the water, it gets carried out. As more fresh water comes in from upstream, more of it dissolves. And so you can imagine that the concentration at this face is going to be constant in time. So C equals constant. The other situation you could imagine is if you dissolve a certain amount of naphtha, say, or gasoline in water, and then you decant the water off that gasoline, and then you dump it into the groundwater. then all of a sudden that's a fixed mass of gasoline that's contained in water, and it's not being replenished in any way by fresh water coming from upstream and new stuff dissolving. So the other boundary condition that you might imagine is the one that's represented in the lower figure, which is exactly the same, is kind of the same process, and that is that you have a spike, a delta function in terms of the concentration. So you introduce the concentration in water at this location at time 0, and then you don't keep on adding it. You only add it once. And if you add it once, I suppose it would be like putting perfume on and walking across the room, in that it moves. No, actually, that's not a very good analogy at all. Unfortunately, the analogy that I would want to use is a bit rude, so I won't use it. If you farted. Farted is a given amount of mass of noxious odors that you put into the air, and it's not replenished, and so it moves downstream. And so you could imagine if you took the concentration of that as you go downstream, it would have a large concentration. If it didn't diffuse, it would, as it was pushed downstream as the wind blew, then it would just move down as a skyscraper and be carried down as that tower. If it diffuses and tries and get rid of this infinite concentration gradient by physically moving to each side, then progressively, as it goes downstream, it will look like a hill that gets lower and lower. And so, again, this would be d star equals 0. This would be d star greater than 0. And this would be d star much greater than 0 in this one. Whoops, no. In this one. Right? Those three. And so that's physically what these this expression represents. And so that's all we need to know, I think, for now. We know we can use these equations, don't need to derive them, need to understand what the terms are. One term represents diffusion, one term represents advection, and the other term represents rates of accumulation. And we can use them to be able to figure out exactly what these concentration distributions look like in an aquifer, which is what this is, and we can also use them to figure out exactly when it arrives and in what concentration it would arrive. And I suppose we could apply the same to this, in that if we look at what these would look like when they arrive, this is the case for diffusion being 0. This is the case for d star being greater than 0. And this would be the d star for much greater than 0. And so it's kind of interesting, right? Because this physically says that this is arriving before the velocity should say that it would arrive, right? It's going at 5 meters a second. It has to travel 5 meters. It should be there in 1 second. But this is saying that it gets there before 1 second. And that's because if you look at it, that has to be the case, right? Because it's diffusing ahead of that front, which is moving at 5 meters a second. And therefore, this would arrive before that. And so it's a little strange in terms of thinking about what that would mean. But it's because it's diffusing ahead of the front. And I suppose the other interesting thing you could imagine here is that if you look at these relative masses that are ahead of the front and are behind the front, then they're of similar mass to each other. They're not drawn very well here, but you'd expect them to be equivalent to each other. The amount that's going ahead of the front should be depleted from the amount that's behind the front. So you'd expect them to be roughly the same masses. And really this height here, whoops. Oh, I don't know why it didn't that. Oh, it did that for some. Oh. So in other words, this height here multiplied by this length over which it occurs, in other words, the area integrated is really equivalent to the mass. Okay? All right, so what else? So we made the case, if I go back to here, that we're interested in these transport mechanisms. We now have an expression that covers both of these, our so-called advection diffusion equation. Certainly includes diffusion and equivalent diffusion in a porous medium. Certainly it includes advection, but we haven't really said much about how that accommodates mechanical dispersion, other than saying that if you look at the effects of this dispersion as it goes mixing downstream, it looks just like diffusion. And so it may be that we can add these effects for diffusion and dispersion together. And of course, this dispersion effect is different from advection. Advection is physically carrying the beaker from upstream to downstream. Dispersion is the process that goes on inside the beaker as it's being carried downstream. And so we might want to understand a little bit about that. And so that comes into basically our physical description of what the causes of dispersion are. And they're pretty straightforward. You can imagine that if you have a porous medium that has lots of fine-grained material and some coarse-grained material, then the pore throats in each of these would be small or large. We know from permeability that the pore throats that are large have high flow velocities in them, and the pore throats that are small have low velocities. And so if you just look at Darcy's law and the rate at which transport would occur in these, then it would move much faster in the big pore throats than the small ones. If you have path lengths in the system which are tortuous, and so some path lengths happen to be long, and some path lengths are much shorter, then again, you'd expect that to be the essence of this effect. And the other effect, which is perhaps a minor effect, is that even within each pores, you can imagine, well, from what you know about the distribution of velocities that occur along a pipe, I think you know that that velocity distribution is parabolic. And so this is velocity, I guess, in the middle. And this is radius across the pipe. So the fastest velocities are the middle. The smallest are at the edge, where the boundary condition is this stick boundary condition or zero velocity boundary condition. So you can imagine that something which is traveling down the tube at the side goes much less far in a given time than the stuff that goes down the middle. And so if you look at the cross-section of the concentrations as they go downstream, you'd expect it to travel less far. And so if you imagine this as acting within a pore, then at the pore scale, you also get these different concentrations existing as well. So some of these things are at very large scale, and some of these things are at small scale, but they're similar processes. And together, they're all processes that contribute to what we'll call mechanical dispersion or hydrodynamic dispersion. They're synonyms of each other. And it just explains this idea of, as you go downstream, and you start off with this distribution that looks like Manhattan, concentration versus radius, then it takes on two forms. If you draw a cross-section across here and look at it, this would be the distribution of concentrations because of this lateral spreading. You know, they go further, they diverge, the flow paths diverge, and it moves laterally from here. And longitudinal dispersion is that if you draw a section along here from A to A prime, if you like, which would be A to A prime, then you'd expect that the high concentrations due to this go to lower concentrations here at the front. And so there are two effects. There's this longitudinal spreading, which is, if there's no longitudinal spreading, I suppose you'd expect this to look like plug flow, and this to look like plug flow as well. And so this would be if D star lateral was equal to 0, and this is if D star longitudinal was equal to 0. Another plug flow, no dispersion. And if there is dispersion, then you get the red lines. And that's physically what's going on. And so because it looks just like diffusion, then typically in this advection diffusion equation, this term here ends up being substituted by something that accommodates for two effects. The effect one is diffusion, which is fixed law, modified to account for the fact that the diffusion has to occur in these tortuous flow paths in a static fluid. And the second one is mechanical dispersion. And the idea is that we can link these two things together into a single coefficient which represents these two effects. And if we put it in a single coefficient, then when we solve the equation, we solve it with this effective coefficient included in them. So that's the only point that I'm trying to make here. And this coefficient we will refer to as, so this is what we refer to as d longitudinal, and this would be d transverse. And they are described in this form. So d transverse would be equal to diffusion, effective diffusion, plus alpha transverse times the flow velocity. And this longitudinal term would be equal to diffusion term, effective diffusion, plus coefficient of longitudinal dispersion multiplied by the advective velocity of the system. So those are perhaps two important terms. They're also mentioned again on this sheet, but I'll just outline them and note a few things about it. And so you see that there's a multiplier on these of velocity. And so if you imagine that the advective velocity is 0, this whole second term drops out, and it's only the diffusion that exists, which happens to be a small number. So typical values of d star might be order of 10 to the minus 9 meters squared per second. Maybe 10 to the 8, maybe 10 to the 10, doesn't matter. But they're very similar to the magnitudes of free diffusion of a compound in water. And they're quite small. And so if the value of this is 0, then this doesn't matter. But if the value of this is even a small velocity, and progressively larger velocity, then this second term becomes more important. This term doesn't change, and so at some stage this term completely swamps the response. And so it represents these two behaviors. When it's stagnant, diffusion dominates, and this right-hand term is 0. And when it's moving, diffusion stays small, and this term becomes finite and large, and therefore it dominates the response. And so what we'd like to be able to do is figure out exactly what the magnitude of this term is for longitudinal and transverse dispersion, because it defines this shape that is present in here, which we think is useful to us. And then if we know that, then we know how to be able to calculate this term. And if we know how to calculate this term, then we can use it in this expression to be able to calculate exactly what this profile looks like in our aquifer, and also what the downstream arrival timing and concentration history would look like as it arrives. So that's basically what we want to do. The one thing it's probably worthwhile noting is that this is the advective velocity in the downstream direction, in the longitudinal direction. Obviously, if the net flow in this is from left to right, the transverse velocity is 0. And so using this as a velocity of 0 isn't very helpful. So this is always the longitudinal velocity. So that's worthwhile noting. I suppose the other thing that's clear from this is that the units from this are meters squared per second, and the units of velocity are meters per second, then the units of this have to be in units of meters, right, by definition. Yeah, okay. And the values of this are surprising. Actually, the values are just equal to the plume, some fraction of the plume length, but we won't talk about that now. So I guess this says more about it. Maybe we've explained all of this. So that this makes sense, I suppose, we could explore by looking at some laboratory data. And the laboratory data would be as these ones down here. So this is out of Fetter, the book that you may or may not have. And we only need to look at one of these maybe. So what is this? This is an experiment. So you can imagine an experiment where you take a core. How are we doing for time? Oh, we've got 5 minutes anyway. And just like the core that we've taken before, we could imagine doing an experiment where upstream we define the concentration changing with time as we turn on the concentration. So this is time. Along the length of the core, we look at the concentration, and at the downstream extent of the core, we look at the arrival time. So this is time, length, and time. All of these are relative concentrations. And so if we look at what the transport along the core looks like, then we know it looks like this if it's plug flow. And we know as it arrives downstream, it will look like this again if it's plug flow. If it's not plug flow, it would look like this. And if it's not plug flow, it would look like this. Right? So this is the, if you like, the spatial, and this is the temporal response. So this is how the concentration rises as you're there to greet it, or it comes you're there to greet it. So initially there's no concentration. As time goes on, it builds until basically the plug has worked all the way through. And so what you could do is you could do some experiments in the lab to look at either the distribution of the concentration in the core, not very easy because you can't see into it, or look at the concentration as it arrives downstream in your beaker as it comes out of the core. And so if you take this response and you fit it to the response that you expect, and from that model it with this equation to figure out what the effective diffusion coefficient is. So in other words, by changing the values of the diffusion coefficient, you should be able to get all of these different profiles and all of these different arrival profiles. And so these arrival profiles that you get will be indicative of the value of this effective diffusion coefficient which the aquifer is seeing. And so if you figure out what that effective diffusion coefficient is in this experiment, then you could plot the value of that effective diffusion coefficient as a function of some parameter. So you measure the effective diffusion coefficient, and you do the experiment at a velocity equals 0.001 meters a second, 0.01, 0.1, 1 meter a second, probably don't, etc., but you get the idea. So you do it at a whole bunch of different velocities. So you'd expect that this would change from being plug flow when it's at this velocity to being highly canted over as you have a much higher velocity. And then this effective longitudinal diffusion coefficient you get, you do two things. You divide it through by the diffusion-only diffusion coefficient, and you plot it against the advective velocity, which you know because you run these experiments and applied it, the length of your specimen, which you know because you run the experiment, and the magnitude of d star, the diffusion coefficient. Here is d sub d, which is just the diffusion coefficient for diffusion only. And you plot these data for the measured one that you get relative to diffusion only, and you plot it as a function of changing these velocities. And these are the data you get. These are the data points. And not surprisingly, you see a couple of distinct features. The first feature is that, as you'd expect, at very low flow velocities, which are what these are, you'd expect that the diffusion coefficient you get would only be the diffusive diffusion, no advection terms. So the value of this coefficient you expect would be 1. And so you kind of get that. It's a little less than 1, but not more. As you get progressively higher and higher velocities, then the magnitude of this advection affected one is probably going to be larger than that because we expect it to conform to this expression here. And so at higher velocities, we get a trend, which if I draw the line through it, should be a line at 45 degrees. So in other words, this goes 1 log cycle over and 1 log cycle up. So it's 1 to 1. And it's basically saying as you take the velocity and you increase it 10 times, then you increase the dispersion 10 times. And so if you look at this relationship here, this is saying exactly this. You increase the velocity 10 times, this is a constant, you increase the effective dispersion amount 10 times. And so that's where this expression comes from. Doing an experiment, plotting the data in an interesting way as a function of normalizing it with the diffusion coefficient and looking at the effective dispersion that you measure in the sample, plotting these individual points, and then figuring out exactly what the equation is that fits through that line. And actually the equation that fits through that line is exactly this, right? It's dl over d star is equal to alpha velocity, I suppose, over d star plus d star over d star. It's kind of a blunt instrument, you see. But otherwise, if I take this equation here, and if I divide both sides through by d star, d star, d star, that's all I've done, then this is the expression you get. This clearly is 1, which is this equation here. And it happens to be 1 because velocities here are very small. And as the velocities get to be larger, then this term here should respond linearly. Double velocity, it should double this value. Triple it, should triple it. And so that's where that comes from. And so this series of experiments really vindicates this way of being able to define this coefficient. And actually, of course, it's the way that someone would have originally discovered that that's the control. Okay. The only interesting, tricky thing here is that we've used this interesting non-dimensional number. It's non-dimensional because velocity is meters per second, dispersion coefficient is meters squared per second, and length is meters. So it has no dimensions. And it happens just to be a useful way of being able to plot it. And this term is actually referred to as Peclet number, after its originator, Monsieur Peclet, Frenchman. and it's a common number that's used in groundwater hydrology, which when it's less than 1, it means it's diffusion dominated. Clay is good things for isolating nuclear waste because all the transport is by diffusion. There is no advection. And advection happens to be a very efficient way of carrying things. And at Peclet numbers larger than 1, it's progressively more advection dominated. And so it's a coefficient that we'll return to in this class. Perfect timing. 1 minute to go. Any questions? Anyone awake? I am.